Welcome back. In this lecture video, we continue looking at the completely randomized design. In particular, we're going to be taking another look at how to perform the calculations required to do an analysis of variance using data from a completely randomized design. Now, in our review, we looked at the calculations that were taught in your first methods course. At least this is the way that I teach this. We know that in performing an analysis of variance, the idea is that we take the total sum of squares, the total variation associated with the response variable, and we partition it into components that correspond to the design of the experiment. All right, and so for the type of experiment, the type of design that was presented in your first methods course, we had two sources of variation. We had variation between samples and we had variation within samples. And so we saw in these notes the computations for partitioning the total sum of squares of the response into those two components which when added together give you back the total sum of squares. Right, so again, the two components that we partition that total variability into are called the sum of squares between samples and the sum of squares within samples. Now, the way that I approach this when I teach the first methods course, notice that the total sum of squares, there are three components here, and we have this equation which constrains the values. If we know two of these values, we can get the third. So for example, the way that I teach this, because I think that to me, it's the easiest way to do it when you're first doing analysis of variance. I teach that you compute the total sum of squares and you compute the sum of squares within, and then you get the sum of squares between by subtraction. Now, again, that is the way that I like to approach this because I think it's the easiest way to do it. And in fact, if I scroll forward here in these notes, we'll find the example where we actually perform this. And so we had this example involving the rice varieties, the 4 rice varieties, and we were wanting to compare the average yield for those 4 rice varieties. And we took these summary statistics and then we used them to calculate the total sum of squares, which we obtained very, very easily. Then we calculated the sum of squares within, again obtained very, very easily from the data given in that summary. And then once we had the total sum of squares and the sum of squares within, we obtained the sum of squares between by subtraction. So the total sum of squares minus the sum of squares within. Now that's not the only way to do it. What you can do, you can also calculate the total sum of squares and then the sum of squares between using the formula from a previous slide. And then once you have those two, calculate the sum of squares within by subtraction. So that's another way to do it. And what we're going to look at in this particular lecture video utilizes that approach, where we compute the total sum of squares. We then compute the sum of squares between, and then once we have those two, then we can calculate the sum of squares error, or the sum of squares within. Now, the reason that we're going to be looking at this other approach, this second approach, is because as we generalize to different kinds of designs, randomized complete block designs, designs involving Latin squares, and so forth, it's perhaps going to be a little bit easier to use this other approach that we're going to look at today. And so that's the purpose for looking at this. Now, before we get into it, I want to look at an analogy with the sample variance. Now, you're familiar with the sample variance, and you know that the sample variance, denoted by s squared, is given by the following expression, s sub xx divided by n minus 1, and n minus 1 being the degrees of freedom associated with the sample in this case. And this quantity s sub xx is given by definition by this expression here. So it's the sum, I going from 1 up to the sample size. It's these of the squared deviations from each observation, or of each observation from the sample mean. All right, so you're familiar with this quantity. This is the numerator for the sample variance, and this is called the corrected sum of squares. You may have heard of that term. Now, when we say corrected, we don't mean that we're correcting some kind of a mistake. What that terminology means is that we are calculating squares, but after we have subtracted off the mean of the sample. So by correction, we're talking about subtracting off a quantity, all right? And in particular, in this case, correcting for the mean. Now, you're probably also very familiar with the computational formula, or the shortcut formula for the variance, given by this next expression: the sum of the squared x values minus 1 over n times the square of the sum of the x values. So that is a computational formula that is often used. In many cases, it's going to be easier to use this computational formula than it will be to use the definition formula for the sample variance, because you don't have to subtract the mean from each of the observations to do this calculation. Using the definition formula, you have to subtract x bar from each of the sample observations, square those deviations, and then add those deviations up. And so you have n subtractions to do. With this computational formula, there's only one subtraction that you have to do. Otherwise, all you have to do is add up the squared values of the x's, add up the x's and square that sum, and then you, from the sum of the squared values, you subtract 1 over n times the square of the sum. Okay, so in the context of that expression, the sum of the squared x values is called the uncorrected sum of squares, and it's uncorrected because, again, we've not subtracted off the mean first. All right. Now, the quantity that we subtract from the uncorrected sum of squares is called a correction factor. Okay? And so in this expression here, the correction factor would be 1 over n times the square of the sum of the x values. Now, we can also represent this computational formula in the following way. USS for uncorrected sum of squares minus C being this correction factor. And this is the type of terminology and notation that you're going to see in the context of experimental design. All right? Almost always. In textbooks and so forth, when they talk about how to do the analysis of variance calculations for the various kinds of experimental designs, they're almost always using these computational formulas. All right, and so that is, I just want you to be familiar with this kind of a breakdown and this kind of terminology, because it shows up all over the place. And so the application of that to ANOVA, we're going to use the same type of terminology and computational formulas, or shortcut formulas, in calculating the various quantities needed to perform analysis of variance for each of the various designs that we're going to be investigating. And so, again, we're going to be talking about calculating sums of squares, or uncorrected sums of squares, and also correction factors that we then subtract from the uncorrected sums of squares. Now, we'll be using these kinds of computational shortcuts to facilitate partitioning the total sum of squares of the response variable into the sources of variation that are associated with the treatment structure and the design structure that comprise the various experimental designs that we're going to encounter as we go forward in the course. Now, to kind of get used to this, we're going to do this first for the design that we already know how to do the calculations for, which, as we discussed, is the completely randomized design. All right, so let's take a look at this. So for the completely randomized design, with respect to now the analysis of the data, in order to perform an analysis of variance using data from a completely randomized design, or CRD, the following types of summary statistics will be needed. In general, two broad types of summary statistics. We're going to have sample summary statistics as well as overall summary statistics. Now, notation and formulas for these summary statistics at the sample level and overall are given on the following slides. And so let's first look at sample summary statistics. And so we're talking about organizing the data and summarizing the data. And so at the sample level, we're going to be computing the response variable totals. All right, and so here I'm using the variable y to represent the response variable that's being measured. And so for the ith sample, the sample from the ith treatment group, let's say, the response total for that sample is denoted y sub I dot. Okay, now just let's take a look right here. This is what the observation, how that observation is denoted. The observation for the jth experimental unit that has received treatment I, where I goes from 1 to t. I is so t is the number of treatments. I is the index I corresponds to which treatment the experimental unit has received. All right, and then J is the particular experimental unit within that treatment group. R sub I is the number of, it's the sample size for that treatment group, right? Or in other words, the number of replications for the ith treatment. And so with that, in order to get the response total for the ith treatment sample or ith treatment group, we just add up those responses. All right, and so we're adding up y sub ij, where j goes from 1 up to r sub I. All right, so I is not varying here. I is fixed. It's either, it's from this set of values 1 through t. And in order to not have to write down this, it's just, we know what this means, but it's a bit cumbersome to write down, especially when you've got to write down a lot of these kinds of quantities. We're going to use a shorthand that is utilized a lot in statistics. And we're going to represent this using a dot for the index that we're summing over. So in this case, we're summing over the second index, which I'm denoting by j here. And so to denote that, what I'm going to do is I'm going to replace j with a dot, okay, as I've done here. And so the way we read this is that we've summed up the observations for the ith treatment group, and we've summed over all of the observations in that sample. All right, and so that is the response total for the ith treatment group. So y1 dot would be the response total for the first treatment group. Y2 dot would be the response total for the second treatment group, and so forth on up to y sub t dot, which would be the response total for the tth treatment group. Again, r sub I is the number of replications for the ith treatment group. All right, and then we have the means associated with each of the samples, and so we will denote the mean of the ith treatment group by y bar sub I. All right, that is just the response total divided by the number of replications for that treatment group, and so we can write it in either of these two ways. All right, but notationally, we're going to denote it by y bar sub I. And then finally, we may choose to represent the uncorrected sum of squares for the ith treatment group using this kind of notation. So again, this would be the sum, j going from 1 up to r sub I, of the squared responses in the ith treatment group. All right, and so we may choose to, in some cases, represent that as USS sub I. Okay, next looking at the overall summary statistics, right? So putting all of our data from the various samples into one big bucket, one combined sample, and then computing summary statistics for that combined sample. These are the calculations, the kind of summary statistics that we will need. So again, we will need the overall response total. And since we are summing over both indices now, I'm going to denote this by y sub dot dot. So y sub dot dot is the total of the responses across all treatment groups. The total number of replications we will represent this way, r dot, all right, because we are summing up the number of replications across all samples. In other words, we are summing over the index I. And then finally, we're going to need the overall mean of the combined data. And what we'll do is denote that by y bar bar. All right, so not a single y bar, but 2 bars. And this is just the sum of all of the observations divided by the total sample size, all right, which we can represent that expression using the summation notation. But you can see that it is, somewhat cumbersome. It's more easily represented using this simplified notation. All right, so this is really pretty standard notation that you see in experimental design books, and we're going to adhere to that. All right, just makes a lot of sense to do that. And then finally, for the overall summary statistics or the overall combined sample, we will also need the uncorrected sum of squares, which I'll denote this way, USS, uncorrected sum of squares, TOTE, the total uncorrected sum of squares. And again, that's just the sum of the squared values of the observations across all samples. Okay, so with that in mind, and also with the discussion that we just had, this analogy with the sample variance and how we can calculate that and think of that calculation in terms of an uncorrected sum of squares minus a correction factor. Let's now look at how to do the calculations for an analysis of variance for data from a completely randomized designed experiment. And so the first thing we would have to do is to calculate the correction term, and we denote that by C. And you can see here that the correction term is equal to the square of the total of all the observations across all samples. All right, and then the denominator of this correction factor is the total sample size. So this should look this is essentially the same exact quantity that we talked about in the context of the sample variance. All right, so the correction term, the correction factor that we subtract off of many of the quantities, as you'll see, is the square of the total of the responses across all samples divided by the total sample size. So it's a very easy quantity to calculate. Next, once we have the correction term, we can calculate the total corrected sum of squares. Right? When we talked about ANOVA before, we called this the total sum of squares. But I'm going to throw in here the word corrected, because once we subtract off the correction factor, then we will have actually have the total corrected sum of squares. And so the way that we do that is to first calculate the uncorrected sum of squares, and then we subtract off the correction factor. All right, and so remember that we're also denoting this uncorrected sum of squares using this notation as well. So what this means is we have to square every observation in every sample, add all those squared values up, and then from that subtract off the correction factor. Now, if you think about it for a second, this is going to be much easier than if we were to calculate the overall sample mean, and then subtract off that mean from each of the observations in every sample, square those deviations, and then add those squared deviations up. That's a lot of work. Using this computational approach, we only have to do the subtraction once, so that saves us a lot of work. Now, in the context of a completely randomized design, remember that we partition the total sum of squares, and in particular the total corrected sum of squares, into two pieces. The component due to the treatments, or the between sample variability, and then the sum of squares within, which we also call the sum of squares error. Now, again, when I first teach this, what I do is I have students calculate first the total sum of squares and then calculate the sum of squares error. And then once you have those two, get the treatment sum of squares by subtraction. But the way we're going to do these calculations in this course, because it's going to be much easier as we look at more complicated designs, we're going to calculate the total corrected sum of squares and then calculate treatment sum of squares. All right, and then once we have both of those, then we will get the sum of squares error by subtraction. So how do we calculate the sum of squares due to the treatments, or the treatment sum of squares? Well, we first calculate this quantity. So what we have to do is square each of the sample totals. Notice that I'm squaring y sub I dot. And if I go back up to go back up here a few slides, y sub I dot is the response total for the ith treatment group. Okay, and so then what we have to do is square each of those totals, divide the squared total by the size of that particular sample, add those quantities up, and then from that subtract off this correction term. Okay, and then once we have both the total corrected sum of squares and the treatment sum of squares, you see that we subtract the sum of the treatment sum of squares from the total sum of squares to get the sum of squares error. Now, once we have those quantities, we can perform the rest of the calculations for the analysis of variance. And it's often easier to do that in the context of the ANOVA table. That's one of the reasons for using an analysis of variance table, not only to present the results, but to facilitate the calculations. Now, let's just remind ourselves of the structure of the ANOVA table for a completely randomized design. Again, we have three sources of variation. We have the total variability, and we partition that into two components: the variability due to treatments and the variability that remains. Right, the unaccounted for the variability in the total variability that is unaccounted for by the treatments. Now, associated with each of those sources of variation, there is a number of degrees of freedom. Recalling that T is the number of treatments being used in the experiment, the number of degrees of freedom associated with treatments is T minus 1. The total degrees of freedom associated with the experiment is equal to the total sample size minus 1. Now, the total sample size in this notation that we're using, that we're starting to use here, and we will continue to use throughout the rest of the course, the total sample size is R dot, right? That we're adding up the total number of observations from all of the samples, all right? And so the total number of degrees of freedom would be R dot minus 1. The error degrees of freedom can be obtained by subtracting the treatment degrees of freedom from the total degrees of freedom. And if we do that, we see that that turns out to be R dot minus T. So those are the degrees of freedom associated with each of the sources of variation in the first column. Next, we have the column for the sums of squares. In fact, these are the values that we calculated on the previous slide. These are the sums of squares for the various components associated with this design. So we have the total sum of squares down here. Up here in the first, the top row, we have the treatment, the sum of squares due to treatments. Right here, we have the sum of squares error. And so we can calculate these as we showed on the previous slide. Once you have those quantities, then we can calculate the mean squares very easily. The mean square due to treatments is equal to the sum of squares due to treatments divided by its degrees of freedom. The mean squared error which is going to be our estimate of the variance associated with the error terms, is equal to the sum of squares error divided by its degrees of freedom. And then finally, once we have the mean squares, we can calculate the F statistic by dividing the mean square due to treatments by the mean squared error. So that is the notation and the approach, which is slightly different than the way at least the way that I teach it in my first methods class. Right, the way that I teach it in that first methods class really goes along with how we describe the analysis of variance procedure. But now that we're getting into more complicated, or we will be getting into more complicated designs, we need to look at a slightly more efficient way of doing the calculations. And so that's what we've looked at, and we have seen the notation that we're going to be using as we go forward. Now, the next thing we want to do is talk about data organization. It's going to be make our job easier if we organize the data in a particular way. So data from a completely randomized design is conveniently organized in tabular format, one column for each sample or treatment level. Now, the required sample summary statistics that we've looked at previously are then computed as column summary statistics. The required overall summary statistics are computed as overall table summary statistics. And so the required summary statistics that we've just been discussing are very easily calculated when we organize the data in the correct way. So let's take a look at what that organization looks like. All right, so here we have, for a completely randomized design, a very nice way to organize the data. So in the body of the table, we have the actual data. We have a column for each of our treatment groups or samples. And you'll notice here that the number of observations within each sample can vary. R1 is the number of observations in treatment 1. R2 is the number of observations receiving treatment 2, and so forth. All right. For each of these columns, for each of these treatment groups, we have summary statistics down here. I've listed 4. We said that we were going to need the sum, the treatment sum for each of the treatment groups. And so I've got that first. We also need to know the number of replications, and so I've got that listed second here. Once we have those, it's very easy to calculate the mean. All we have to do is divide the sum by the number of reps, and that gives us this quantity here. And then we will also need the sum of squares, the uncorrected sum of squares of the observations within that column of data for that sample. All right, and so we'll put that uncorrected sum of squares down here. All right, so this would be y11 squared plus y12 squared plus and so forth down to plus y1 r1 squared. All right, for sample 2, we have the same kinds of quantities, and we continue on and calculate those summary statistics for each of the samples. All right, and then we also need overall summary statistics, and those are very easily calculated once we have the summary statistics for the individual samples. The first is the overall or total of the observations across all samples, and that's again denoted by y dot dot, and that's just the sum of the values in this row, right? So it's the sum of those quantities there. Likewise, the overall sample size, r dot, is the sum of the values in the sum of the sample sizes in that row. Now, once we have the response total across all samples and the total sample size, it's very easy to calculate the overall mean by dividing r dot dot by y dot dot by r dot. And then finally, to get the total uncorrected sum of squares, all we have to do is add up the uncorrected sum of squares for each of the samples. And so that so 3 of these rows are row totals. This particular cell right here, the y bar bar, is the ratio of the total of the responses to the total sample size. Now, regarding the quantities down here in the last row, the uncorrected sum of squares, if we wanted, we could also represent these using this notation here. All right, it doesn't really matter, but the other notation, it's getting a bit busy there. But we know what these correspond to: the uncorrected sum of squares for the sample 1, the uncorrected sum of squares for sample 2, and so forth. And then we have the total uncorrected sum of squares. All right, so this is the organization that we're going to use for data from a completely randomized design. And organizing the data in this way greatly facilitates calculating the basic summary statistics that we'll need in order to do an analysis of variance. And once we have these quantities, then it becomes very easy for us to continue on and finish out the calculations for the analysis of variance. So let's look at an example. This will be example 2.2. In the previous lecture video, we looked at an example. I'm not sure that I gave it a number. All right, we'll call that one 2.1. This will be 2.2. And this is going to be the example that we looked at in our review. All right, we've already looked at this example, but we're going to redo it using the calculations that we have looked at, and you can then compare the results that you got using these calculations to what you got before. All right, so an experiment was conducted to compare the yields of 4 varieties of rice, each of 16 plots on a test farm where soil fertility was fairly homogeneous, was treated alike relative to water and fertilizer. Each of the 4 varieties of rice was randomly assigned to 4 plots on the farm. The yield in pounds per acre was recorded for each plot. Now, because the variety was assigned to 4 plots completely at random, this experiment has a completely randomized design. Now, notice here, they talk about each of the 4 varieties of rice was randomly assigned to 4 plots on the farm. There is no mention here of any kind of restriction on that randomization. And so that tells us then that the treatments, the varieties of rice, were assigned completely at random. And so this is a completely randomized design. Now, notice also that in the statement of the problem, it says that on this test farm, soil fertility across the farm, across the plots used in the experiments on this farm, they're all fairly homogeneous. All right, and that's an important consideration. A completely randomized design is appropriate when the experimental units that you're using in the experiment are homogeneous. If the experimental units are not homogeneous for some reason, and in particular, if you can identify the reason that they are not homogeneous, then you should probably not use a completely randomized design. All right. For example, and it's very common in agricultural studies that on farms and things like that, that there will be differences in soil fertility, differences in the level of moisture, differences in gradients in plots and things like that. And because of that, it can be very difficult to find a large number of plots that are all homogeneous. It may be much easier to find to find groupings of plots that would be homogeneous. Maybe on one part of the farm, you've got some plots that are homogeneous with respect to themselves, but on another area of the farm, you've got plots that are different from the first group, but they're similar to each other. And so in that kind of a situation, a completely randomized design would really not be the most effective. You would probably want to use something like a randomized complete block. And so that's one of the reasons why we need to understand and know about other kinds of designs, because the simplest design that we've looked at, the completely randomized design, is typically, especially in agricultural studies, is not going to be the most effective. What happens is if you have heterogeneous experimental units and you use a completely randomized design, then you do not have the ability to account for the variability in the various experimental units. And all of that unaccounted for variability goes into the error term. When it goes into the error term, the variability associated with the error term increases, and having an error term with a large amount of variability, in other words, having a lot of unaccounted for variability in your data, is going to diminish the power of your hypothesis test and decrease the precision of your estimators. All right, and so that's not a good thing. And so one of the main purposes of this course is to look at various kinds of experimental designs that will allow us to account for, control and account for variability that is not due to the treatments, but due to the experimental material itself. And if we can account for that, to the extent that we can account for that variability, that extra variability, then we can improve and increase the power of our tests and the precision of our estimators. Okay, now the raw data along with summary statistics are provided on the next slide. So in the body of the table here, we have the actual raw data, all right, and then for each of the samples, I have computed the various summary statistics that we require. In particular, the sum of the observations, the number of reps, the sample mean, and then the sum of squares for the values in each of these samples. Once we have the sample summary statistics, we can calculate the overall summary statistics as well. All right, and so just what I would recommend is go ahead and doing these calculations, making sure that you get the same answers that I've got here. All right, now we've seen the raw data. We see the sample sizes within each of the samples, and we see that the overall sample size is 16. All right, and so given that we have 4 treatment levels and that we have 16 observations, we can start filling in the ANOVA table for this analysis. And it's always a good idea to key out your ANOVA table with the degrees of freedom first, so that you can confirm the analysis once you do it. All right, and so because there are 4 treatment levels, 4 rice varieties, we know that there are 3 degrees of freedom due to treatments. We know that there are 16 total observations, so there are 15 degrees of freedom total. And then we can get the number of degrees of freedom associated with the error by subtraction. So 15 minus 3 is going to be 12. And so that we can go this far without really having to do much work. But now we need to fill in the sum of squares column. And so let's see about how we do that. All right, so the first thing we need to calculate is the correction term. That is the square of the response total across all samples divided by the total sample size. If I go back up here to my summary statistics, I see that the overall total of my responses across all samples is 15,871, and that my total sample size is 16. All right, and so I square the 15,871, divide by 16, and this is the quantity that I get right here. Now notice, if you happen to have a TI-84, and it's probably going to do this on other calculators as well, because they probably don't even have as many places they can display as the 84. But when I do this calculation on the TI-84, what it displays is a rounded version of that quantity. It actually rounds off to 2 decimal places. Well, no, let me put it this way. It displays. In its display, it rounds off to 2 decimal places. So it only shows 0.06. However, in the internal registers of the calculator, it has the full precision, so it has the 0.0625. So I just wanted to point that out in case you happen to have a TI-84 and do this calculation. It's not going to look quite like this. It's going to round the decimal portion to 0.06. Okay, so that is the correction term. Next, we have to calculate the total corrected sum of squares. And that is obtained by first calculating the total of the squared values of the observations in the combined sample, and then from that subtracting off this correction term. Now let's go back to the table and let's find that uncorrected sum of squares. And again, that is going to be right here, the overall uncorrected sum of squares. Okay, and so that is what we've got here. We subtract off this correction factor, and so we get the corrected total sum of squares. Okay, next we need the treatment sum of squares. What we have to do is square each of the response totals within each sample, divide by the corresponding sample size, add those quantities up, and then subtract off this correction factor. So you see here that we're using this correction factor multiple times. Okay, so what we have to do is we have to square each of these sums. For each sample, square the sum, divide by the sample size, and then we add those quantities up. So when we do that, this is the value that we would get. From that, we subtract off the correction term, and then we get the treatment sum of squares, which is 89,931.1875. Once we have the corrected total sum of squares and the treatment sum of squares, we can get the sum of squares error by subtraction, and so that gives us 49,875.75. So now we have the quantities that we need to fill in the sum of squares column in our ANOVA table. And let me just point out that to start filling the table out in this column, we really only need the total corrected sum of squares and the treatment sum of squares. All right, because once we plug those into the table, we know that we can get this cell, the sum of squares error, by subtraction. Take the total sum of squares, subtract off the treatment sum of squares, all right, which would give us the 49,875.75, which we already calculated, but I'm just saying that we actually would not have had to do that at that point because we can do it in the context of the table. Now that we've got the sum of squares calculated, the hard work is done. We're just about, the rest of it is easy. We really don't even have to remember how to do it really because of the structure of the table. It reminds us to get the mean squared for treatments, we divide the sum of squares for treatments by 3, its degrees of freedom. All right, and we also divide to get the mean squared error, we divide the sum of squares error by its degrees of freedom, or 12. And so when we do that, we get these mean squares. Once we have the mean squares, we obtain the F statistic by calculating the ratio of the mean squared treatments to the mean squared error. All right, and so we get 7.21 rounded to 2 decimal places. Now, if we wanted, we could do all of those calculations outside of the context of the ANOVA table. All right, and so this is, again, how we would do it. But again, the ANOVA table not only gives us a nice way to present the results, but it really facilitates in a very nice way how we do the calculations. Now, let me just show you. Here is a little spreadsheet that I've constructed that has the same format as the data organization table, as you can see here. So here are the data values for the 4 samples, along with the summary statistics that we need to calculate for those samples, and also the overall summary statistics. And then down below, I've got the ANOVA table that I've programmed into the cells, the various calculations that we need. So this, you don't even have to do the calculations by hand if you've got something like this constructed. All right, so from the data organization table, I calculate the correction coefficient. I calculate the sum of squares total, the sum of squares treatment, and then I get the sum of squares error by subtraction. All right, and then based on the structure of the organization table, as well as the total number of observations, I have the degrees of freedom cells programmed in. The sum of squares column gets its values from these cells up here, and then everything else is calculated just the same way we did it when we did it by hand. And so you can see that the calculations are really pretty straightforward to do. The hypotheses tested by the ANOVA, just as a reminder, the null hypothesis is that there are no differences among the population means, in this case the means of the rice varieties. We denote that using the notation this way, mu1 equal to mu2 equal to mu3 equal to mu4, where mu sub I is the mean yield for rice variety I. The alternative hypothesis is the opposite of the null. All right, so that would say that there are differences among the population means. If we were to use a significance level of 0.05, for example, then the critical point for the test is based on an F distribution with 3 numerator and 12 denominator degrees of freedom, which is 3.49. Since our F statistic, which was 7.21, is greater than 3.49, we would reject the null hypothesis at the 0.05 level of significance and conclude that differences exist among the mean yields of the 4 rice varieties. And as we discussed when we reviewed this material back in Module 1, the job is not done at that point. It's really just beginning. If we conclude that differences exist among the mean yields, then the natural follow-up question is, where are the differences? And so with that in mind, specific follow-up comparisons would be motivated and would be warranted because we rejected this null hypothesis that said that they were all the same. Now, again, we looked at how to do specific follow-up comparisons in our review of basic ANOVA back in Module 1, in particular using contrast coefficients, so testing custom hypotheses utilizing contrasts. And so we saw how to come up with the contrast coefficients to do that. We saw how to do it by hand, and we also saw how to use SAS to do that, using the contrast statement, using the estimate statement, and also using the Ellis mean statement. So we know how to do these follow-up comparisons. At this point in time, we're not going to look at that in detail because we've already looked at that. We know how to do that for the completely randomized design, but we will continue to look at how to do follow-up comparisons as we get into different kinds of designs. All right. So the procedure for doing those follow-up comparisons is similar, but there are some differences. And so as we get into different kinds of designs, we'll look at those differences. All right, let's look at another example, example 2.3. An experiment was conducted to compare the yields of 5 lentil varieties. The experiment was planted in a completely randomized design, with each variety replicated 4 times. So this sounds very much like the first experiment that we looked at, the first example. During the growing season, however, livestock broke through a fence and heavily grazed 4 plots before they were detected and removed from the area. Now the yield in kilograms per hectare from the undamaged plots are given in the table on the next slide. The following slide contains a partial ANOVA table with the degrees of freedom filled in. Okay, so the first, the slide with the partial ANOVA table is 2 slides forward. So let's take a look at the data. And you can see here that the experiment was initially designed so that there would be equal replication for each of the 5 lentil varieties, all right? But because of this problem with livestock breaking into the experimental area, all right, and damaging some of the plots, we see that there were 1, 2, 3, 4 plots that were damaged. And so we end up with an experiment that is unbalanced. Now, in some experimental designs, that could cause a problem when it comes to analyzing the data, all right? But with a completely randomized design, that's really no issue at all right? So this is one of the advantages, actually, of the completely randomized design. You don't have to have equal replication. Unequal replication can result from a variety of factors. In some cases, you might want to design an experiment where you've got a control treatment, and you might want to replicate the control treatment at a higher sample size than the other active treatments. But there are also situations just like this where, for whatever reason, some of the experimental units are lost during the experiment through damage or whatever. Okay, but that's not going to affect at all the analysis of the data. So again, what we do is we organize the data in this fashion. Each column corresponds to a sample. For each of the samples, we calculate these 4 summary statistics: the sum of the values in the sample, the number of reps in the sample, the number of observations in the sample, or the number of times that that particular treatment is replicated, the mean of the sample, and then the uncorrected sum of squares of the values in that sample. Once we have those summary statistics for the individual samples, it's very easy then to calculate the overall summary statistics as we've done here. Now, notice that we have a total of 16 observations. It was intended to be 20 observations total, but because of the loss, we have 16 total observations, and we have 5 varieties. All right, and so because of that, we know that the total number of degrees of freedom associated with the data, 16 minus 1, would be 15, and the number of degrees of freedom associated with the treatments or the varieties is 5 minus 1, or 4. Once we have those two values, we can get the degrees of freedom for error by subtracting the 4 degrees of freedom from the 15. Next, we need to calculate the summary statistics that we'll need for calculating the other quantities in the ANOVA. The first term we need is the correction term. Again, that is equal to the square of the total response over the overall samples divided by the total number of replications, or the total number, or the total sample size. And so the total, or the overall sum, is 8,880. So we square that, divide by the total number of observations, that's 16. All right, and so we get this quantity here, 4,928,400 is our correction term. And that's the term that we're going to be subtracting from each of those quantities here to get the total corrected sum of squares and the treatment sum of squares. To get the total corrected sum of squares, we first compute or obtain the uncorrected total sum of squares. That's given down here, the overall uncorrected sum of squares. All right, and then from that we subtract off the correction term. All right, and so we get 422,700. So 422,700 is the total corrected sum of squares. Next, we need the treatment sum of squares. And so to get that, we go back to our table. We square, for each sample, we square the sum, square the total, we divide by the number of reps, and we add those quantities up. All right, and so then we get this quantity here, from which we subtract the correction term. And so this would be our treatment sum of squares. Once we have those two quantities, we can enter them into the ANOVA table along with our degrees of freedom. We obtain the sum of squares error by subtracting the treatment sum of squares from the total sum of squares. Once we have the sum of squares, we obtain the mean squares by dividing the sum of squares by their corresponding degrees of freedom, all right, which we have here. And then finally, we calculate the F statistic by taking the ratio of the treatment mean squares to the error mean squares, all right, and so we get about 6.44. All right, and so you could also do those outside the context of the table, but again, I think it's very easy to do it in the context of the table. All right, and so then here's another example of the spreadsheet that I've constructed. I created the first one, and then once I have that, then I can just I can tweak it. I can add a column, all right, and enter the data values, and everything else gets updated automatically. Oh, one thing I want to point out here is that the p-value for the test is 0.006354. Okay, so again, what hypotheses are being tested by this particular ANOVA? Well, the null hypothesis is that there are no differences among the population means. In this case, there are no differences among the average yields of the different lentil varieties. That's the null hypothesis, and it's represented notationally this way, that the population means are all equal. The alternative would be the opposite of that there are differences among the population means. If we were again to use a 0.05 level of significance, then the critical point comes from the F distribution with 4 numerator degrees of freedom and 11 denominator degrees of freedom. That comes from these two quantities. All right, that value, when we look it up in the table, is 3.36. Since our test statistic, F, which was at 2 decimal places, 6.44, exceeds that critical point, we reject the null hypothesis and conclude that differences do in fact exist among the mean yields of the 5 lentil varieties. Now again, this would be just the starting point of the analyses. We would want to follow up to find out where the differences are. We're not going to do that right now. We will do it as we continue on, and especially as we look at different designs. So that is how we perform the calculations to do an ANOVA in the context of a completely randomized design. Again, you've seen these calculations before, but as we move forward and look at more complicated designs, it's going to be better if we use these shortcut calculations where we calculate the correction factor and then subtract that correction factor off from the various types of sums of squares.